Welcome back to another explainer. Today we're moving way past the magic of AI image generation. We all know the drill, right? You type in a prompt, wait a few seconds, and boom, a stunning image appears. But if you're anything like me, you really want to know what's actually happening under the hood. So we're going to explore the exact architecture and the totally massive compute mechanics of latent diffusion. This is the engine powering everything from Stable Diffusion to the latest Flux models.
Okay, let's dive right into this with a pretty dramatic quote directly from our source material. It says, "Pixel space diffusion on 512 by 512 images is a computational war crime." And honestly, they aren't kidding. Trying to do this the old school way might literally melt your graphics card or, bankrupt you in server costs. It perfectly sets up this massive, seemingly insurmountable compute problem that early AI pioneers faced when trying to generate high-res images from scratch.
To really understand that quote, we got to look at the raw numbers. If you take a standard 500 million parameter UNet model and ask it to run 50 denoising steps just to create a single image, that costs about 5 teraflops of compute. That is 5 trillion math operations just for one image. Now imagine trying to train this model on a dataset of a billion images to actually make it smart. The financial cost of that compute bill becomes absolutely absurd. It's just completely impossible to scale. So how did the industry actually solve this? Here is our roadmap for today. We'll start with the compute problem, uncover the two-stage solution that totally changed the game, see how text guides the process, track the architecture's evolution up to 2024, and finally, look at how we can run these massive models on everyday consumer GPUs. All right, Section 1, the compute problem. Let's look at exactly why raw pixel generation is just so incredibly inefficient. When you run diffusion directly in pixel space, say at a 512 by 512 resolution, your neural network is churning through these massive tensors. We're talking shape B, 3, 512, 512. It's pulling roughly 100 gigaflops for just a single sampling step. But here's the absolute kicker. The network is wasting immense computational power calculating tiny, perceptually unimportant details. It's burning through millions of calculations just to figure out the high-frequency texture of a single leaf in the background, rather than focusing on the actual broader semantic structure of the image.
Which brings us to Section 2, the two-stage solution. This is Robin Rombach's elegant rescue plan that basically became the fundamental recipe for Stable Diffusion.
The solution is this brilliant two-stage process. I like to think of it like a compressor and a painter. First, you take your massive 512 by 512 image and run it through a compressor, a VAE, squashing it way down into a tiny 64 by 64 latent space. Then, your painter, the actual diffusion model, does all of its heavy lifting exclusively on that tiny, compressed canvas. By doing this, you're working with basically 1/16 of the pixels. That translates to about 64 times fewer flops, and you still get comparable image quality. A huge game changer.
So let's break down these stages. Stage 1 is the VAE, or Variational Autoencoder. The main thing you need to know here is that this is trained entirely separately, just once. Once it's trained, it's frozen in place. Its only job is to act as a highly efficient translator, taking that bulky pixel space, crunching it into a dense, information-rich latent space, and then translating it back to pixels when the image is finally done. Then we have Stage 2. This is the actual diffusion model, usually a UNet or more recently a diffusion transformer. This is the network that's actually learning to denoise the data. And here's the really beautiful part. The math, the loss function, it is all completely identical to standard diffusion training. The network doesn't even know it's not looking at pixels. You've literally just swapped the data domain over to the latent space. But heads up, there is a massive pitfall here that trips up engineers all the time. It's called the VAE scaling factor. Because of how the VAE compresses data, you have to multiply or divide the latence by a magic number. It's usually around 0.18, which effectively means dividing by roughly 5.4. If you forget this scaling constant, oh man, your diffusion model will train on latence with wildly incorrect variance, and the entire system will just spit out pure garbage. It's literally a tiny decimal that can make or break the whole architecture. Okay, moving on to Section 3, guiding with text. Now, what's really interesting about this next part is how we actually steer these models with our words to get exactly what we want.
Because how does typing "a cat on a skateboard" actually manipulate the latent math? The answer is cross-attention. As the model is denoising the image, every single block inside the UNet stops and looks at your text prompt. The image features act as queries, and those frozen text embeddings coming from a model like CLIP or T5, they act as keys and values. This cross-attention mechanism is literally the only way your text actually gets in and influences the generated visual features.
But what happens if you just don't give it text? Well, during training, engineers randomly drop the text prompt about 10% of the time, replacing it with a null token, basically an empty prompt embedding. This forces the model to learn how to generate images unconditionally, without any text guiding it. And this null token becomes absolutely essential for steering the image later during inference, which brings us right to the math of guidance. This is classifier-free guidance, or CFG. Think of it like a dial. When you generate an image, the model actually calculates two paths at the exact same time. It predicts the image with your text prompt, and it predicts the image with that null token. CFG uses a mathematical weight, called W, to aggressively push the final result away from that unconditional prediction and directly toward your specific text prompt. It's the dial that controls exactly how strictly the model obeys your words.
And if we look at the extremes of that CFG weight, you can totally see why tuning it is such an art form. If W equals 0, there's no guidance. The model just ignores your text and hallucinates whatever it wants with maximum diversity. But if you crank W way up past 7 or 10, the model overfits to your prompt. The images get deep fried, supersaturated, and take on this artificial, oily look. For production, the sweet spot for that CFG scale is almost always nestled right between 3 and 7.
All right, Section 4, Architecture Evolution. Let's fast forward and see how this core two-stage recipe scaled incredibly fast from 2022 to 2024. And this brilliantly illustrates the massive leap in scale over just 2 years. In 2022, Stable Diffusion 1.5 used an 860 million parameter unit with a single clip text encoder. By 2023, SDXL jumped to 2.6 billion parameters. And then in 2024, models like Flux.1 Dev just completely shattered the ceiling. We're talking a massive 12 billion parameter multimodal diffusion transformer, or MMDT, paired with heavy-duty T5 text encoders.
So to summarize this macro trend quickly, the industry is basically replacing UNets with diffusion transformers because they just scale so much better. They're using massive language models like T5 to make sure the AI actually listens to your complex prompts. And they've expanded the latent space from 4 channels to 16 channels to give us incredible detail headroom. Yet, despite all these massive upgrades, the underlying two-stage latent architecture remains exactly the same as that original 2022 recipe.
Finally, Section 5, running on consumer GPUs. How on earth do we bring this massive compute requirement down to a local dev laptop?
This is the 8GB consumer GPU challenge. Normally, running a 12 billion parameter model like Flux requires extreme model parallelism on massive enterprise-grade H100 server GPUs. Trying to cram all that into a standard 8GB graphics card? That's a high-stakes engineering puzzle right there. But, you know, the open source community is amazing, and they figured it out, using a very specific 3-step sequence. It really all comes down to a rhythm of execution. First up, staggered loading. You don't need everything sitting in memory at once. You load the text encoders, encode your prompt, and then, this is crucial, you delete them from VRAM. Then you load the massive DIT, denoise your latents, and delete the DIT. Finally, you load the VAE to decode. Combine that rhythm with 4-bit quantization using tools like bits and bytes to cut memory usage by 8 times, plus dynamic CPU offloading to automatically swap modules in and out of the GPU, and boom, that is exactly how you fit a supercomputer model onto a laptop. Okay, before we wrap up, if you are out there building your own pipelines, let's run through a rapid-fire checklist of crucial production pitfalls so you don't completely break your code. First, never forget that VAE scale mismatch we talked about. Seriously, remember the 5.4 division? Second, ensure your text encoders are actually loading. If Stable Diffusion 3 falls back from T5 to CLIP, your prompt fidelity will absolutely crater. Third, do not mix latent spaces. A LoRa trained on SDXL will absolutely not work on SD3 because the VAEs are completely different. And finally, negative prompt leaking. Remember that an empty negative prompt defaults to the null token, but a filled one changes your entire unconditional baseline. They are definitely not the same thing. So, we've gone from the raw compute bottleneck of pixel space diffusion to the elegant 2-stage latent solution, all the way to squeezing 12 billion parameters onto a standard consumer GPU. Which leaves me with this provocative thought to leave you with. If a 12 billion parameter transformer can run on an 8GB laptop today, what is the next computational workaround we're going to have to solve tomorrow? Are we talking full generative video, real-time 3D environments? The architecture is definitely going to keep evolving, and we'll be right here to explain it when it does. Thanks for joining me on this explainer today. Keep exploring, and I'll see you next time.